The goal of ENME489Y was to explore the fundamentals of remote sensing. During the semester-long project, students used LiDAR and computer vision principles to create 3D point clouds of various targets on University of Maryland's campus. The project gave students experience not only in the fundamentals of remote sensing, but also in system design and data analysis in Python and MATLAB. Remote sensing is the collection of information about an object or phenomena without making physical contact with that object. Typically, radiation interacts with the target, altering the radiation's properties. Recording and analyzing this radiation allows some information about the target to be measured. In this class, we mainly discuss LiDAR, radar, and computer vision. There are two main methods of remote sensing, active and passive. Passive sensing does not generate the radiation that interacts with the target, but rather uses naturally occurring radiation such as sunlight. Active sensing uses self-generated radiation such as laser light, radio, acoustic, or microwaves. Light detection and ranging, or LiDAR, is a type of active remote sensing. The generated radiation is laser light, which after being transmitted is reflected off the target and then received by a sensor. The range equation, C delta T over 2, determines the distance between the target and the receiver using the speed of light, c, and the time it takes the laser light to travel to and from the object. Often, LiDAR systems will include sensors that give other information about the object, such as GPS to record the target's location, or an inertial measurement unit to record the LiDAR system's orientation. Computer vision is a method by which computers can gather data from digital images and videos. This is an important aspect of the project, and in this early step, I demonstrate identifying the color green using Python and OpenCV, a programming library used mainly for real-time computer vision. As you can see, the code tracks the color green as it moves throughout the Raspberry Pi camera's field of view. This is done by setting the HSV color values of the color I would like to track in order to create a mask and isolate this color from the rest of the image. A similar method will be used to identify the red laser line when mapping my target. The sensor design used a 3D printed mount on which were attached my line laser, the transmitter of the system, powered by an Arduino, the Raspberry Pi camera, or the receiver of the system, and the Raspberry Pi, which along with my laptop was used for data acquisition and analysis. I used an Ethernet cable to share internet with my Pi from my laptop. The Arduino and Raspberry Pi were powered by a battery bank which sat on the tripod, and I used my phone attached to the 3D printed tripod mount as my IMU in order to record the angle of my system. For software, I used a combination of Python and OpenCV for data acquisition and analysis, along with VNC Viewer and CyberDuck to access the Raspberry Pi from my laptop and for file transfer. This system uses a geometrical lidar technique that relies on the distance between the camera and the line laser. The line laser reflects off of the object, and the center of this line can be seen in the camera's field of view and identified using color masking in OpenCV. As the object moves further away from the camera and laser setup, the reflective light moves closer to the center of the camera's field of view. This is because the camera's field of view widens at further distances, so the number of pixels the laser appears from the center of the camera decreases as the object moves further away. This can be analyzed in OpenCV by calculating the number of pixels from the center that the laser light appears in the camera. To demonstrate this technique, a single beam configuration like the one diagrammed here was set up. The object was moved from 0 to 10 feet away from the system at 6-inch increments, and the location of the laser return was tracked and recorded with OpenCV and Python. As you can see from the video recorded, the laser return moves closer to the center of the camera. The distance of the target from the system and the number of pixels from the center of the camera's field of view that the green laser appeared were graphed on top of the theoretical curve in Excel. The experimental and theoretical data were reasonably close, so now we move on to the line laser calibration. First, I had to align the line laser with the camera in order to obtain the most accurate data. To do this, the video feed from the Raspberry Pi camera was displayed with a number of green vertical lines. I then put the line laser in its position on the 3D printed mount and rotated it until it aligned with these green lines, and hot glued it in place. A similar calibration was done with the line laser as was done with the single beam laser. This time I moved the system from 0 to 10 feet away from the wall at 6-inch increments. The calibration code run on the Pi saves a JPEG image for each distance from the wall at the user's request. These images were then transferred from the Pi to the laptop, and another Python code employed an HSV mask for the red laser, averaged the red pixels together to find the center pixel, and saved the wall distance and corresponding pixel location in the text file. I then plotted this experimental data on top of the theoretical data, saw that they were reasonably close, and was able to move on to mapping a test target. For my test target, I'll be mapping this container. I chose it mostly because it's white, so the red laser light should show up well on the camera. Some features I'd like to see are the rounded edges, the transition from the square body to the rounded top, and hopefully the indentation for the handle right here. To map the test target, I ran the data collection code on my Raspberry Pi by establishing a VNC connection from my laptop. This code saves a JPEG image for each desired angle with the angle as the file name, allowing me to map the test target from top to bottom. As you can see, I checked the angle displayed on the Bubble Level app on my phone for each new JPEG image. Here you can see that the data collection code displays each image on the screen, allowing me to check the image before saving it. This was before I began using an Ethernet cable, and my Pi's internet connection was not very reliable, resulting in disconnections while collecting data. In order to generate a 3D point cloud of my test target from the JPEG images, I first found the color mask values for the red laser line with the color picker code, which allows you to change the upper and lower bounds of the HSV color mask and displays the original image and mask results in real time. After transferring the JPEG images to my laptop, I then ran the data generation code in PyCharm. This code cycles through each JPEG image for each angle, blacking out the right half of the image, which does not contain the laser line, and blurring and converting the image to the HSV color space. It can then apply the HSV color mask using the bounds entered by the user and employ the geometrical lidar principles along with the angle and the file name to apply an X, Y, and Z coordinate for each pixel with a red laser return. These coordinates save to a text file in order to generate a 3D point cloud. Once this file is moved to the MATLAB directory, a 3D point cloud can be generated by plotting the X, Y, and Z coordinates. As you can see, all the expected features are visible in the point cloud, including the curved sides, round top, and handle indent. After verifying the functionality of my field deployable LiDAR system indoors, I was able to begin mapping my on-campus target. For my target, I selected the ATM outside of Ellicott Hall. I chose this target because I thought its boxy shape would be easily identifiable in a 3D point cloud while still having interesting features. Some of these features include the blue overhang at the top, the light boxes on all four sides, the AC unit in the back, and the front alcove. I decided to map each of the four sides of the ATM individually and rotate and combine these 4 point clouds into one point cloud at the end. I began by mapping the back face of the ATM, which had the least amount of ambient light. I used the same data generation code used to map the test target and saved a JPEG image for each angle. The 3D point cloud generated for the back face turned out pretty well on the first attempt, with the exception of the overhang. Originally, I thought this was due solely to its dark color, which makes the laser light not show up very clearly in the camera lens. But I realized later this could be addressed by mapping the overhang separately, allowing the camera and laser to be slightly closer to this part of the target. I began mapping the left and right faces of the ATM in the same manner in which I mapped the back face. However, when I compiled this data, I did not get a 3D point cloud which looked like my target, but rather random points which seemed to project outward from the camera lens. I thought this issue may be due to the ambient light coming from both the lighting of the ATM and the spotlight on the left side of the ATM, because when I applied color picker to these JPEG images, I did not get clear laser lines for many of them. So I decided to map again, but this time blocking out as much ambient light as I could. I covered the glass panels which were allowing the ATM lighting through to the left and right sides, and this time when I ran color picker, I was able to see very clear laser lines. However, when I created the 3D point cloud, I was getting the same effect. At this point, I realized I was mapping at a range of slightly over 10 feet, which was too far away for the camera to detect the laser line pixels moving across the screen. I began remapping at a closer distance and was able to achieve a 3D point cloud that looked like the side of the ATM. Unfortunately, I was never able to get a 3D point cloud of the front face of the ATM as there was far too much ambient light that could not be blocked out. On my Raspberry Pi, I found the HSV color mask values for each of these 3 data sets, and after transferring the JPEG images to my laptop, I ran the data generation code for each face. I then imported these text files into MATLAB and rotated and shifted the left and right faces according to where my LiDAR system was when the data was being collected. This is my first unfiltered point cloud of my target. As you can see, the overhang is not very clear and the walls of the ATM are not very straight. In order to generate a more accurate point cloud, I realigned my laser with the camera before each mapping and moved as close to the ATM as possible. I also split up mapping the body of the ATM and the overhang for the left face, not only so that I could map it from a closer distance, but also to avoid pointing my system at a spotlight on the side of the ATM. I also made sure to keep my system orthogonal to each wall of the ATM while mapping by placing ground markers. These mappings resulted in this unfiltered point cloud of 3 sides of the ATM. As you can see, it is a much clearer point cloud than the original one. Unfortunately, you cannot see the light boxes on any of the faces or the overhang on the back wall, but you can see the overhang on the left and right and very clearly see the AC unit on the back. Each point cloud contained erroneous points in front of and behind the wall faces. So I indexed these points in these areas that lay below the overhang and removed them. For the back face point cloud, I had to make sure not to remove the points showing the AC unit, so I removed this area from my indexing. Filtering in MATLAB resulted in this point cloud. I've mapped each face in a different color so that they are easily identifiable. This is the same point cloud, but color varies with height. The features of the ATM are much more visible without the erroneous points, and hopefully this point cloud will create a better mesh. Originally, I had done this filtering along with the rotation and stitching together of the 3 point clouds in Cloud Compare before generating my mesh. Cloud Compare has a lot of intuitive tools that allow you to do this filtering and stitching by hand, including a snip tool to remove points in areas where they don't belong, and a translation and rotation tool that allows you to orient multiple point clouds with one another. However, writing the MATLAB code to do this for you is a much cleaner and more automated method of achieving the same result. It also can take into account the location at which data was collected from in order to more accurately align individual point clouds. To begin meshing my final filtered point cloud, I first imported the point cloud into Cloud Compare. I then computed the normals for the mesh and used the preset number of neighbors, which was 6. I applied a Poisson surface reconstruction to generate a mesh, but the resulting mesh had a lot of empty space, which was anticipated because the points making up the 3 faces of the ATM are far apart. However, I recomputed the normals, this time with a much higher neighbor number, and remeshed in hopes of filling in some of this empty space and connecting the sides of the ATM with one another. As you can see, the resulting mesh has much less empty space as the left and right faces of the ATM were connected to one another. You can see the protrusion of the AC unit on the back face and the overhangs on the left and right faces, all of which were visible in the 3D point cloud. However, you cannot see the front face or the back overhang as these could not be accurately mapped. You also cannot see the light boxes, although the indent where they should have been appear on the overhangs.